What if everything you learned about energy is wrong? Not wrong in the details, wrong in the most fundamental way possible. Here's what I mean. Right now, your phone is using energy. The sun is radiating energy. Your body is converting energy from food into motion, into heat, into thought. We talk about energy constantly. It's everywhere in physics, in chemistry, in everyday life. We build entire economies around it. We wage wars over it. We design technologies to harness it, to store it, to transfer it from one place to another. But here's the uncomfortable truth. Energy is not a thing. It doesn't exist the way you think it does. And I know that sounds insane. How can energy not exist? You feel it when you're tired, when you've run out of energy. You see it when lightning strikes. You pay for it every month on your electric bill. Scientists talk about it like it's one of the most fundamental concepts in the universe. But stay with me, because once you understand what energy actually is, once you see past the language we use to describe it, you'll never look at the universe the same way again. When you flip a light switch, we say energy flows from the power plant to the bulb, traveling through wires, carried by electrons, lighting up your room. When you eat breakfast, we say your body extracts energy from food, breaks it down, releases it, uses it to power your muscles, your brain, your heartbeat. When a car burns gasoline, we say chemical energy converts to mechanical energy. The fuel releases its energy, the engine captures it, the wheels turn. The language itself tricks us. Every single phrase makes energy sound like a substance, like water flowing through pipes, like something you can hold, something real that moves from place to place, something with physical existence. But think about it more carefully. Have you ever actually seen energy? Have you ever touched it, held it in your hand, isolated it in a jar? No, you've never seen energy. You've seen motion. You've felt heat. You've observed light, heard sound, watched things change position or temperature or state. What we call energy is really just a mathematical relationship between these observable things, a number we calculate, a pattern we've noticed. And here's where it gets strange, where the whole framework starts to feel less solid than you thought. Let me show you what I mean. Consider a pendulum, just a weight on a string, swinging back and forth. Simple. Something Galileo studied 400 years ago. At the top of its swing, the weight is high up but moving slowly. We say it has gravitational potential energy. Lots of it. At the bottom, it's lower down but moving fast. We say it has kinetic energy. Lots of it. And as it swings, we say energy transforms. Potential becomes kinetic. Kinetic becomes potential. Back and forth. Back and forth. Now here's the question that should bother you. What exactly is being exchanged here? What substance is flowing from potential to kinetic? Think about it. Really think about it. Nothing. There's no substance. There's no fluid draining from one reservoir into another. The pendulum is just swinging. That's all that's happening physically. A mass moving through space under the influence of gravity and tension. The mathematics happens to work out that if we assign certain numbers to certain configurations, if we calculate 1/2 mv squared for the motion and mgh for the height, those numbers add up to a constant. The sum doesn't change as the pendulum swings. We call that conservation of energy. But the energy itself? It's not a thing. It's a number we calculated, a relationship we noticed, a pattern in the mathematics. And this bothers me. It should bother you too. Because we've built this entire conceptual framework, this vast edifice of theory and technology, around something that isn't real in the way we think it is. So what is energy actually? This is where it gets interesting, where you start to see what's really going on. Energy is a bookkeeping device, an accounting trick, a brilliantly useful one, maybe the most useful concept in all of physics, but a trick nonetheless, a way of keeping track of what's possible and what's not in the universe. When we say a system has a certain amount of energy, we're not describing a stuff it contains. We're not pointing to some glowing essence sitting inside it. We're describing its capacity to cause change, its ability to do work, to rearrange itself, to affect other things. Think of it like money in an economy. You can't eat a dollar bill. You can't burn it for warmth, at least not effectively. Money isn't inherently valuable. It's paper, or increasingly, just numbers in a computer. But it represents the ability to exchange goods and services. It's a tool for tracking value, for making transactions possible, for comparing different things on a common scale. Energy is the same. It represents the ability to cause change. And just like money must be conserved in a closed transaction, what you spend someone else receives, no dollars disappear into nothing. Energy must be conserved in physical processes. The mathematical forms are deceptively simple. For a moving object, kinetic energy is 1/2 mass times velocity squared. For an object in a gravitational field, potential energy is mass times gravitational acceleration times height. But these aren't formulas for stuff. They're formulas for relationships, for possibilities, for what configurations are allowed, and which aren't. And here's the beautiful part. Here's why this accounting trick works so well, that it fooled us into thinking energy is real. In 1915, a mathematician named Emmy Noether proved something extraordinary. Something that changed how we understand conservation laws forever. She showed that every symmetry in nature corresponds to a conservation law. Every regularity, every invariance in the laws of physics gives rise to something that must be conserved. Time symmetry. The fact that the laws of physics don't change from one moment to the next, that an experiment done today gives the same result as the same experiment done tomorrow, gives us energy conservation. Space symmetry. The fact that physics works the same here as it does over there, that the universe doesn't have a preferred location, gives us momentum conservation. Rotational symmetry. The fact that there's no preferred direction in space gives us angular momentum conservation. Think about what this means. Really sit with it for a moment. Energy isn't conserved because there's some cosmic accountant checking the books. It's not conserved because there's some law preventing it from being created or destroyed. It's conserved because the universe is the same now as it was a moment ago. Because time is uniform. Because the fundamental laws don't change. Conservation of energy is really just a statement about the deep regularity of time itself. And that's profound. That's much deeper, much stranger, than saying energy is some kind of fluid that can't be created or destroyed. When you drop a ball and it falls, we say potential energy converts to kinetic energy. The ball speeds up as it drops. The numbers shift from one column to another in our accounting ledger. But what's really happening? Physically, in the actual universe, the ball is simply following the geometry of spacetime, taking the path of least action, doing what comes naturally given the curvature of space and time around Earth. The energy framework is our way of describing this mathematically, of predicting what will happen next without having to solve complicated differential equations of motion. It works brilliantly. But it's not describing a thing. It's describing a pattern. Now, we speak of different forms of energy, as if there's a whole zoo of different types. Kinetic, potential, thermal, chemical, electrical, nuclear, electromagnetic, elastic, gravitational. The list goes on. As if these are different types of stuff, different flavors of the same substance. But they're not. They're not different substances at all. They're different ways of accounting for motion and configuration at different scales. Different bookkeeping categories for the same underlying physical processes. Thermal energy? That's just the random kinetic energy of countless molecules bouncing around, vibrating, spinning. There's no special thermal substance. No caloric fluid flowing from hot to cold, like scientists thought in the 1700s. It's just molecules moving. Chemical energy? That's electromagnetic potential energy stored in the configuration of electrons around atomic nuclei. It's about how particles are arranged relative to each other, not about some chemical essence they contain. Nuclear energy? That's the strong force potential energy in the arrangement of protons and neutrons in the nucleus. The same idea, different force, different scale. Strip away the labels, peel back the layers, and you find it all reduces to a few fundamental interactions and the geometry of spacetime. What we call energy is simply our way of tracking how these interactions play out over time, of predicting what configurations are possible and which aren't, of knowing what can happen and what can't. Consider a battery. We say it stores chemical energy, as if there's some energy stuff packed inside, waiting to be released. But open it up. Look at the atoms and electrons with the most powerful microscopes we have. You won't find little packets of energy sitting there glowing, waiting to be used. What you'll find is a configuration of matter, zinc and copper, acid electrolyte, electrons arranged in particular ways around particular atoms, a configuration that, when connected to a circuit, will naturally evolve toward a different configuration, one with lower potential energy. And in doing so, in making that transition, it can push electrons through a wire. The energy is just our way of quantifying this tendency, this potential for change, this capacity to do work. It's not a thing you can bottle. It's a description of what will happen if you close the circuit. And here's where people get really confused, where the language completely breaks down. They ask, when we use energy, where does it go? When you drive your car, when you charge your phone, when you turn on the lights, Where does the energy go? This question itself reveals the confusion. The category error we're making. Energy doesn't go anywhere because it's not a substance that travels. It's not a thing that moves from place to place. What happens is that organized, useful motion gets converted into disorganized, less useful motion. Concentrated configurations spread out. Order becomes disorder. When you burn gasoline in a car engine, we say chemical energy converts to mechanical energy and heat. But what's actually happening at the molecular level? What's really going on? Gasoline molecules are breaking apart. Long chains of hydrocarbons splitting into smaller pieces, carbon dioxide, water vapor, other products. And when those bonds break, when the molecules reconfigure, the atoms move faster. They have more kinetic energy. Some of that motion gets channeled into the organized movement of pistons, up and down, driving the crankshaft, turning the wheels. That's what we call useful work. But most of it, maybe 70 or 80%, just makes everything jiggle randomly. The engine block heats up. The exhaust gases rush out hot. The surrounding air warms. That's what we call waste heat. The total amount of energy, the total of all our accounting numbers, stays the same. Conserved, as it must be. But its quality degrades. It spreads out, becomes less concentrated, less organized, less able to cause further change, less useful to us. This is the second law of thermodynamics, the law of increasing entropy. Energy doesn't disappear. It just becomes less useful, less available, more spread out across the universe. Imagine a perfectly wound spring, coiled tight. It has potential energy, we say, the capacity to do work. Let it unwind. The potential energy becomes kinetic energy of motion. The spring spins, maybe drives a mechanism, maybe just flails around. But eventually, always, friction converts that motion into heat. Random molecular jiggling. The spring warms up slightly. So does the air around it. So does everything it touched. The energy is still there, still conserved. You can add up all the numbers and they still equal what you started with. But now it's so spread out, so disorganized, distributed across billions of molecules, that you can't use it to do anything useful anymore. You can't gather it back up. You can't rewind the spring with it. It's like dropping a glass of ice water into the ocean. The cold water doesn't disappear. The molecules don't vanish. But they mix with the ocean water, spreading out, warming up slightly, until you can't tell where they are anymore. The information is lost in the chaos. That's what happens to energy in every real process. It doesn't disappear. It just becomes useless. Now, in 1905, Einstein changed everything with one simple equation. 3 symbols. E equals mc squared. This wasn't just saying that mass and energy are related, that you can convert one to the other, like converting dollars to euros. It was saying they're the same thing, viewed from different perspectives. 2 aspects of the same underlying reality. A hot object weighs more than a cold one. Not much more. The difference is imperceptibly small for everyday objects, but it's real. Why? Because thermal energy, the random motion of molecules, contributes to the object's inertia, its resistance to acceleration, its mass. Mass, it turns out, is just another form of energy accounting. Or, perhaps more accurately, energy is a property of mass and momentum together. When matter and antimatter annihilate, when an electron meets a positron, we say mass converts to energy. Mass disappears, energy appears, but nothing is really converting. Nothing is transforming from one substance to another. The system is just rearranging itself into a different configuration, one where the rest mass of the particles is gone, but the kinetic energy of the resulting photons, the gamma rays flying away at the speed of light, is higher. The total energy momentum 4 vector is conserved, as it must be, as Noether's theorem guarantees. The deeper you look, the more you realize that mass and energy are just different aspects of the same underlying reality, the curvature and dynamics of spacetime itself. And this is where I have to be honest with you. This is where it gets uncomfortable, where my understanding breaks down. If energy is just a bookkeeping device, just a mathematical tool we invented, why does it work so incredibly well? Why can we predict, with extraordinary precision, everything from planetary orbits to chemical reactions to the output of nuclear power plants, all using energy calculations? I've thought about this for a long time, years. And here's what I think. Though I could be wrong, the universe has deep mathematical structure, regularities, symmetries, patterns that hold across vast ranges of scale and condition. The laws of physics are written in the language of symmetry and conservation. That's not poetry. That's literally how the mathematics works. Energy conservation emerges from time translation symmetry. The universe is indifferent to when something happens. As long as the laws don't change with time, energy must be conserved. This is why energy is so powerful as a concept, not because we're tracking some real substance flowing around the universe, but because we've discovered a deep pattern in nature, a regularity so fundamental, so universal, that we can exploit it to make predictions without knowing all the details. Energy conservation is one of the most powerful tools in physics precisely because it's so abstract, so removed from the messy details of what's actually happening. You don't need to know every force acting on every particle. You don't need to know every interaction, every field configuration, every detail of a system. You just need to know the initial and final states. And the mathematics, through Noether's theorem, through the symmetries of spacetime, guarantees certain relationships will hold. That's astonishing when you think about it. That abstraction, that distance from physical reality, is what makes it powerful. But here's what bothers me. And maybe this bothers you too. Maybe it should. We still don't know what energy fundamentally is. We have this mathematical framework that works perfectly. We can calculate, predict, design, build. But does that tell us what energy is at the deepest level? Does it tell us what the universe is really doing when we see this pattern we call energy conservation? No, it doesn't. We can describe how energy behaves. We can write down the equations. We can calculate how it's conserved in every interaction. We can predict outcomes with incredible accuracy. But why does mass curve spacetime in a way that conserves energy? Why do the symmetries of spacetime give rise to these conservation laws in the first place? What is the universe really doing? I don't know. And I don't think anyone does. Maybe energy is an emergent property. Something that appears at macroscopic scales but has no meaning at the most fundamental level. Maybe at the Planck scale, at the smallest distances and times, energy isn't even a useful concept. Maybe spacetime itself is made of something deeper. Something we haven't discovered yet. Quantum loops, vibrating strings, something else entirely. And energy is just a shadow of that deeper reality. An approximation that works at our scale. Or maybe I'm thinking about this all wrong. Maybe the question itself doesn't make sense. Maybe asking what energy is like asking what 7 is. It's a concept, a tool, nothing more. But that's where we are. We have a tool that works. We don't fully understand why it works so well. And we don't know if there's something deeper beneath it. So where does this leave us? What do we do with this knowledge? Energy doesn't exist. Not as a substance. Not as a thing you can point to and say, there it is. That's energy. It's a conceptual framework. A mathematical tool for describing and predicting change. An accounting system for tracking what's possible in the universe. And yet, paradoxically, it's one of the most fundamental concepts in all of physics. One of the most useful ideas humans have ever developed. The universe doesn't care about our concept of energy. It just evolves according to its laws, following the geometry of spacetime, respecting the symmetries that govern it, doing what it does. We humans invented the idea of energy to help us make sense of these patterns, to predict what will happen next, to build technologies, to understand nature. And here's the beautiful part. Here's what makes this whole thing remarkable. This fiction we created, this accounting trick, this mathematical abstraction, turns out to be so perfectly aligned with the deep structure of reality that it's become indispensable. Every technology you use, every physical process you observe, can be understood through the lens of energy. Your phone doesn't really consume energy. Nothing is being consumed, destroyed, used up. It rearranges electrons, converts organized electrical flow into disorganized thermal motion, heats up your pocket. But we describe it as using energy, because that framework helps us design circuits, predict battery life, optimize performance. It's useful. The sun doesn't radiate energy. Nothing is radiating out from it, like a substance. It converts mass into kinetic energy of particles through nuclear fusion. 4 hydrogen nuclei become 1 helium nucleus. The mass difference appears as motion of photons and neutrinos. But we describe it as radiating energy because that helps us calculate how long the sun will shine, how much power reaches Earth, how plants can photosynthesize. The framework works. Even your body doesn't extract energy from food. Nothing is being extracted. It breaks down complex molecules into simpler ones, uses the change in configuration to drive other chemical reactions, ultimately converts everything into heat that radiates away. But we say you need energy to live because that framework helps us understand nutrition, metabolism, why you get tired, why you need to eat. It's a useful fiction. The next time someone tells you to conserve energy, or talks about renewable energy sources, or worries about the energy crisis, remember what they're really saying. They're not talking about stuff. They're not worried about running out of some substance. They're talking about maintaining our ability to cause useful change, about keeping the accounting books balanced in a way that benefits us, about ensuring that we can continue to rearrange matter in ways that we find valuable, about having access to concentrated, organized configurations of matter that we can let evolve toward less organized configurations while extracting useful work in the process. Energy doesn't exist. Not really. Not as a thing. But the patterns it describes, those are as real as anything in the universe. Maybe more real than the things we think of as real. And we're still learning what that really means.